points. So, okay. So the function f defined by, I'm going to give you this function here. So find the derivative of f. Alright, so if I rewrite this using a 1/2 power, what rule do I have to use to find the derivative of this? The chain rule. Which says we have to take the derivative of the outside, which is the 1/2, so we bring that down to the front, and we subtract 1 from it, so it becomes negative 1/2. Leave the inside alone, times the derivative of the inside. So this is that chain rule thing we just talked about. Don't forget to do the derivative of the inside. Should be negative 2x. So if you simplify that, you would get, if you multiply the outsides together, 1/2 times negative 2x would be negative x. And then I could put this back on the bottom under a square root. 25 minus x squared.
As long as what you wrote.
As long as what you wrote that is equivalent to the answer, you don't have to simplify it.
Because I wrote negative x times 25
Yep.
minus x squared.
Yep, that's perfectly fine. They would not count off for that. Alright, so part A, and you don't have to have this, they're just repeating it from the problem. This is what you have to have. So negative x over the square root of 25 minus x squared. Or you could leave it like this. Right? Either of these is acceptable. And that's 2 points. Right. Alright, and then part B, you get to use your answer from part A. So this is kind of what I was talking about. Let's say that you didn't get part A right. You messed up the derivative. You didn't do the derivative of the outside or something. So when you go to do part B and you find the slope of your tangent line, you're plugging into the wrong derivative, you can still get full credit for part B. As long as you do the steps of part B right, even if plugging into part A was wrong. Does that make sense? So in part B, to write an equation for a tangent line, you're going to use point slope, which means that you need a point and a slope. And they give you the x coordinate. So you just got to find the y coordinate and the slope and plug in. So to get the y coordinate, we just plug into the original function. So I plug negative 3 in, I'm going to get 4. And then to get the slope, we plug into the derivative, which if I plug into the derivative, I'm going to get a negative negative 3, so 3 over 4, so 3/4. So y minus 4 equals 3/4 x minus x. So 2012. So this part would have been worth another 2 points. Finding the slope and writing the equation for the tangent line. And again, you don't have to solve for y. You can leave it in point slope. So that's also acceptable. So really those first 2 parts, that's 4 points, and I don't think they're really that hard to do. So they were kind of nice on this one last year. Hopefully they'll do it like this again. It would be nice. Okay, so part C. What'd you mess up?
Well, I did everything right, and then when I got to the, I was figuring out my slope. I got 3 times 25 minus 9 to the negative 1/2.
Right.
I changed that to a square root, but instead of moving it to the bottom, I just
left it there.
By
Let's see what they would
3,
do.
so I ended up with a slope of 12, but everything else I did correct.
I would guess on that they would give you, I would guess that they would give you one of the 2 points.
Okay,
If you plug into point slope correctly, that you would still get that
The
point.
derivative of negative 3
Is a point, is a separate point. So if you don't get that part right, you can still get the answer right. as long as you use whatever slope you found. Okay. Part C, let g be the function defined by, and it's a piecewise function. The first piece goes from negative 5 to -3 using this function. And then the second piece goes from -3 to +5 using this function. Is G continuous at x equals -3? Use the definition of continuity to explain your answer. Okay, so the definition of continuity, this is way back. This is like one of the very first things that we did last semester. Like after we introduced limits, continuity was the second thing that we talked about. In order for a function to be continuous at a specific value of x, in this case at -3, the limit, well, let's say as x at c, we'll say it's some x value. So the limit as x approaches c has to exist. The function has to exist there, and those two things have to be equal. Right? So there has to be a limit there has to be function value there, and those two things have to match. So the way that we prove this with piecewise functions is this. To prove the first part, we just plug that value into both pieces and they have to be equal. For the limit to exist at -3, that means that -3 plugged into both pieces has to give you the same thing. So when I plug -3 into each of these, f of -3, we already saw was 4. We already did that. And then when I plug -3 into the second piece, -3 plus 7 is also 4. So the limit as x approaches c exists because the two pieces are the same value.
So how would you justify your answer? Like if you didn't
I
have the
personally
limit
would
part?
list these 3 things and then show step by step
Oh.
how each one, just show that I understood what the 3 things were I had to prove and that I could prove them. That's what I would do. So this one, if you remember the definition of continuity, is a really easy one to get. But if you don't remember it, yeah, so if you can just say yes or no, that's going to be probably a point, and then proving it will be another one. So f of c exists, so that just means plug -3. In this case, we're doing g, but if I just plug -3 in, so if you look at your piecewise function, you plug -3 into the first piece. This says you'll use the first piece for values that are between -5 and -3, including -5 and -3 because of the bars. You'll use the second piece if you're plugging in something between -3 and +5, including 5 but not -3. So
there's a point for considering one-sided limits and a point for
that's
the
these. These are the one-sided limits. Right? Because we're saying this would be the limit of -3 from the left, because this piece applies for everything from -3 to the left. And then this is to the right. And the function exists there. And since all of these were equal, this is true also. So it is continuous. Let's see. So yeah, I mean, even if you don't use this, all of this technical writing, this is basically just saying, we plug -3 into the left-hand piece, which is this one, we get 4. We plug -3 into the right-hand piece, which is this one, we get 4. So, you could show that without using all these little limit signs. So the limit is 4. So the limit exists and it's 4. And f of -3, or in this case g of -3 exists, it's 4. And so those two things are equal. So g is continuous at -3. You don't have to be this formal if they can see that you understand the concept. So now here's the problem. I don't know that if you just put yes that you would get a point at all, because it says answer with explanation. So I think you'd have to have some kind of explanation for that one. Okay, part D, you have to integrate that. And when we integrate it, I'm going to rewrite this using a 1/2 power. What do we have to use? u substitution, because we have one function inside of another one. 25 minus x squared, and you can see it a lot better over here, is inside the square root function, or the 1/2 power function. So when we do u substitution, we have to make sure that the derivative of the inside, which is what we call u, the derivative of the inside is present on the outside. So the derivative of the inside would be negative 2x. So we have to give ourselves a negative 2 and balance it with a negative 1/2. So then we can integrate. So I would have, come down here, negative 1/2. When I integrate something to the 1/2 power, it goes to the 3/2 power times 2/3, right? So when I integrate u to the 1/2, right, because I don't integrate the inside, I integrate the outside. So when I integrate u to the 1/2, I get u to the 3/2 over 3/2, or 2/3 u to the 3/2. I leave the u on the inside. And then the negative 2x dx go away when I integrate, because they're part of the derivative. And when you integrate a derivative, it cancels out. So we've got negative 1/3 times 25 minus x squared to the 3/2. And we're going from 0 to 5. So negative 1/3 times 25 minus 25 to the 3/2 minus negative 1/3 times 25 minus 0 to the 3/2. Right? If I plug 5 in, I'm going to get 0. If I plug 0 in, I'm going to get 1/3 times 25 to the 3/2. But you could leave it like that. 25 to the 3/2, that means the square root of 25 cubed, which is 125. Right? 5 cubed, 125, yep. So 125 over 3. Alright, so let's see what that was worth. So it's 2 points for the antiderivative, which this would be the antiderivative, which we wrote. Oh, they do, okay. You don't have to do it this way. They did, some teachers teach that when you do u substitution, you finish the problem using the u. I don't teach it that way. I don't like it that way. So what we have is okay. Let me try to think of a way to, yeah, they're not going to make you keep the u's. What you could do with u substitution is up here, if I say that this is u, I can plug these numbers in and get new bounds and work the whole problem with u as my variable and never go back to x, as long as I change these bounds. Some teachers teach it that way. I don't. I don't like it that way, because you have to remember to change the bounds, and I just think that there's lots of places for error. So even though it's kind of hard to tell that we did it right, because they have the u change, you don't have to do it that way. So we did the antiderivative right. What they would look for on the antiderivative would be this. Yeah. And then a point for the answer. So how'd y'all do on that one?
I got 6 or 7.
Out of the 9?
Yeah.
That's really good.
Because the last one, I originally answered 0 because I didn't use my 0, but then before we went over it, I was like, oh crap, 0 actually looks like that.
I think I got 4.
That's really good. 4 is good. 4 is very good. 6 or 7 is like really, really good. So, okay, let's see. So let's look at 2011, number 6. 2011, number 6. Kind of a similar idea here, in that you're like kind of just doing a little bit of function analysis here. So look at that one.